Hello, welcome to another tutorial on SimMEEG. Today we're going to be covering how to use SimMEEG as it is integrated within Brainstorm. If you haven't already done so, I would recommend that you download and install Brainstorm and follow some of the tutorials that they have here on the webpage. If you're already a user of Brainstorm and have it installed, if you've updated your recent versions, SimMEEG is actually already installed in there, and we'll show you how to activate that. For information about SimMEEG, SimMEEG can be used actually as a standalone, and you can install it yourself. But if you are a user of Brainstorm, you can use it within Brainstorm, and we'll show you how to do that now. So to start up Brainstorm, go to your Brainstorm directory. You type in Brainstorm. So this is the MATLAB interface here. And it will start the program. And you'll have a pop-up come up like this. So this is the Brainstorm interface. We'll get to making a protocol in a minute, but if you click on plugins here and you go to simulation, if you have the new Brainstorm version, you'll see this simulation SimMEEG. It might be installed. If it's not, click on install. It will download the necessary software from GitHub and install it. And the button should be clicked on load, so you see a little green filled circle here saying SimMEEG is loaded. If it's not loaded, I'm just going to unload it, so it'll show up as a red circle. So just go and click on load. We're going to create a new protocol here. We'll call this SimMEEG tutorial, and we'll use the default anatomy. You can use the individual anatomy for this purposes of this tutorial. We're going to use the default, and we have that come up as protocol. We're going to add a new subject. We'll just keep it simple, subject 1. And in SimMEEG, we're going to be forward projecting our source data, so we need a forward model. We also need to know what sensors we're using. For this demonstration, we're just going to use some EEG. So we go and we click. We'll create a new folder for a new condition. We'll say new condition. We'll keep most of the things default just for simplicity here. Now we need to load in some EEG sensors so that SimMEEG knows how to forward project these sources that we're going to be simulating. So I'm just going to go here, click the ICBM 152, BioSemi 128. You can select any one of them. You can also load in your own EEG locations. Now what we need to do is create a head model for that forward projection. So right-click, compute head model. And it asks for the standard anatomy. We're just going to say yes. Everything looks like the locations. All of them are in proper orientations. And here's the thing that we need to do and consider. We're going to create a head model for our forward projection. When we do this, the sources within the brain are going to be forward projected to the scalp surface, the electrodes on the scalp surface. We need to consider if we're going to be doing inverse solutions, so the reverse of the forward solution, we need to have the head model to be different than what we used in the forward solution. And the reason for that is that in reality, we do not have the forward solution for each individual. If we did, we would need inverse solutions. So we use an inverse solution. The grid points for where the dipoles will be placed and their orientations, if you're going to be using constrained orientations, we don't absolutely know. So we would be cheating the system basically and getting better results doing an inverse solution using the same head model in the forward solution and the inverse solution. So make your decision. Do you want to use a cortical surface for doing the forward projection or a volume? For this, I'm just going to show you how to do it using the cortical surface, and then you can do your inverse solutions using an MRI volume, or vice versa. It's totally up to you. So here we go. It'll take a little bit of time. Just going to use the defaults here to create this head model. I'll press pause here and come back when it's done. Okay, great. That OpenMEEG has now created a head model based on the cortical surface. Now what we can do is we can use SimMEEG to simulate EEG signals. And the benefit for using SimMEEG when you're doing this, kind of the whole point of SimMEEG, is that you will have ground truth known So if you apply any analysis to that, you will know exactly what source's activity looked like, and you can see whether or not your analysis software is doing what it's supposed to be doing. So how to open SimMEEG is you then just go to your new condition, right-click on it, and you'll see this Simulate Signals down here at the bottom, SimMEEG. Click on that, and it's going to start loading in SimMEEG. There will be terms of use. You can accept. If you decline, you won't be able to use SimMEEG, obviously, but we'll just go ahead and accept that. And it's going to load up, and it takes a minute or so to load up. It's going to load up the head model that you just created into the software. So once that little pop-up display goes away, you can start using SimMEEG. Now there's a tutorial on how to use SimMEEG, and I recommend you go and take a look at that. That's at the website here, BrainLab Software, and if you just scroll down, there's a tutorial on how to use SimMEEG, and it goes through all the different functionalities. I'm just going to quickly go through and create some source activity and project that to the EEG sensors, and then we can call that back into Brainstorm. So with SimMEEG, we have a time frequency plot here for source 1, 2, and 3. We select our time frequency region of interest. That's going to be 12 to 15 hertz, but I'm just going to change this down to a single frequency of 10 hertz. And we have power in our post signal activity here, which is going up, but we also have this pre and post activity, which is also high. We're going to make this so it's event-related amplitude enhancement, so formerly known as ERS, event-related synchronization, and we're going to do that for all the sources here. Well, I'll show you how we can do event-related desynchronization or event-related. So you keep the pre-activity high, and that on onset you reduce the signal activity to 0, and then you'll end up getting this event-related decrement in power. And we're just going to keep this as having an increase in amplitude relative to the onset of some event. So now we've got that source power 1, 2, and 3. SimMEEG was designed to do phase locking value and phase lag index. That's why there are only 3 sources. Future versions of SimMEEG will add other triplets, so you can keep on adding as many sources as you like, but currently we're limited to 3 right now, and that's due to the interactions of the phase locking signals and phase lag index and how it's calculated. So I'm going to bypass these for simplicity and brevity of this tutorial. SimMEEG can also do phase amplitude coupling between sources and within sources. We'll bypass that as well. And this will now go into how we're going to be doing our simulation of MEG or EEG. Currently we have EEG loaded up. So here's our forward model panel. We have our MRI loaded based on what was loaded into Brainstorm, as well as the sensors, 128 sensors. Our head model was created using OpenMEEG. So there are 128 sensors by 3 orientations by about 15,000 dipoles for the lead field, and these are based on the cortical surface. Had you done the volume, the MRI volume, this would switch to MRI volume. Currently these are the source locations, but we can click on source locations. That will open up this MRI viewer where you can click and drag different sources. So I'm just going to go to source 1, and you can click and drag that anywhere. I have put in here default locations, which are 2 auditory and 1 visual, but you can click and drag and move that anywhere you like. We're just going to click and drag that to the outer part of the cortical surface. When you're happy with what you have, hit Save Location. That will update those locations in SimMEEG. So we can just go ahead and close that and then replot, clicking on plot, and now that plots the locations of those dipoles in a 3-dimensional head down here at the bottom. And currently we can turn sensors on and off or labels, so now we just see the sensors, and there are the locations. You can also change the transparency of the different volumes here. So now we can really see our source locations and our EEG electrodes there. So these are the locations of where we're going to be putting those event-related power changes of the sources 1, 2, and 3. First, we need to simulate those sources. So this is just the parameters to simulate. They're actually not the waveforms yet. What we need to do is go simulate sources. Just click on update parameters, simulate sources. And if you notice in the MATLAB window, there'll be some output here saying how it's done and doing some intersource correlation, so you can see how correlated these sources are. That's for another tutorial, but we'll take you back to this panel. So now we have our sources simulated. If we click here on our waveform data, source 1, up here this is the pre-post activity. So that's related to this flat line that we have here. We didn't have any pre-post activity. And then we have our signal, so we get this event-related amplitude increase. The light gray lines there, those are the individual trials, and the dark, thick green line, that's the evoked activity, so the average of those light green trials. This is the addition of pre-post plus your signal. So that's for source 1, source 2, and source 3. Now we're going to learn how to forward project this to the sensor data at the EEG electrodes. We want to do this so that we can project just the signals, but we also want noise because the EEG has noise in it. So we can simulate that noise using different types of noise. SimMEEG currently has synthetic sensor noise, synthetic brain noise. So if we did this, you can select how many different brain locations there are, whether they're random locations, and then what the noise amplitude would be. The type of noise that you put in there, whether it being a broadband, wideband, that's all selected up here in the study parameters. So you can do broadband, narrowband, notchband, and pink. So we're just going to select with pink. SimMEEG will have in the future an MVAR and a generative adversarial network, which is an artificial intelligence way of synthesizing brain noise. Or you can load up real sensor noise. But for the sake of this tutorial, to keep it short, we're just going to use synthetic sensor noise, and we're going to hit simulate. Now that's simulating pink noise 1 over f raised to the power of 1.8 here in each one of those sensors. So it's not really spatially temporally correlated. Probably not the best approximation of brain noise, but for the simplicity of this demonstration, we're going to keep that. The next thing that we need to do is to project that source activity from sources 1, 2, and 3 through our forward model onto the surface of the scalp at those electrode sites. So we simply go simulate MEEG, and it's forward projected. So now if I click on A1, A01, we now have the noise. This is the noise data, the 1 over f raised to the power 1.8 at sensor A01. And then we have the signal as it's projected from those 3 dipoles. The overall EEG, which you would record if you were doing this in a human subject, was you would not be able to split the noise and the signal, obviously. You'd be recording the noise plus the signal. So this is the actual EEG signal down here. And we can see that for different electrodes. Now in SimMEEG, what we can do is we can set the different signal to noise ratio. So currently it is set at -7 dB. So we can make this increase in signal to noise ratio by making it -4 dB. Just go ahead and click simulate MEEG again, and then click on your electrodes, and you can see that the noise is reduced. Signal stays the same because we haven't changed the signal parameters yet. And we can make this really noisy. Let's go -14, and then you can see there's a lot of noise now in the recordings here. We'll just go back to something with a fairly high signal to noise ratio, -4 dB, simulate that. And so what we've done now is we've essentially simulated our EEG. We can also in SimMEEG do a lot of analyses, which will be in another tutorial, but we can do our own inverse solutions, which we have here, selected here, which use field trips, or our own in-house ones using beamformers, and select the different parameters. We can also do seated functional connectivity once we have the source inverse solutions conducted. I won't go into that with SimMEEG because this is a tutorial on how we integrate SimMEEG with Brainstorm. We're not going to get into this. We'll do that in another tutorial. Brainstorm also has some great inverse solutions, as well as a plethora of different analysis techniques and methods and grouping statistics. So this is to show how we can integrate SimMEEG with Brainstorm. One last thing on SimMEEG is that it can do Monte Carlo simulations as well. Going back to the SimMEEG simulation of the EEG, we've now simulated the EEG. To get that back into Brainstorm, we simply close SimMEEG, and then a pop-up will come up. So this pop-up will allow you to import the SimMEEG output. The sense final, that's the actual EEG final with the signal plus the noise. The SIG final, those are actually the source signals. And there's the final one, there's the waveform, there's a pre-post wave, there's the noise at the source. Whenever it says sense, that's at the sensor level. Whenever it says SIG, or pre-post, that's at the source level. So we can also load up the sense noise, but it's usually the sense noise final, that's after the processing has happened. We can also load in the sense signal projected data. So we can load in those three. We'll click OK. Now that is importing all of that from SimMEEG into Brainstorm. And so if we go back to Brainstorm here, we'll see these different files for the 90 trials for the sense final. That's the EEG. Note there is a little bit of a bug feature. Just click off that pop-up there. So we can take a look, double click on it. We have our sensors, our electrodes for that trial 1. And we can also look at just the noise, so that's just the noise. Or we can look at just the signal. So this is the signal projected to those sensors. So now you know ground truth, and you can go and do all the analysis that you would like in using Brainstorm with all of the different functionality. You can do filtering, averaging. So basically what you have here with the sense final, it's like you've recorded EEG from a participant, and you can perform all of your analysis as you would in Brainstorm as any other data set. So I'm going to leave you with that, and I hope you enjoy using SimMEEG as it's integrated into Brainstorm.